Hello guys, my name is Bhupesh Asu and we will be talking about the last topic of this PCM. In PCM we have already understood that pulse code modulation system there will be a quantization levels. In the last chapter, in the last our video, we have already discussed this factor. So whenever we are doing uniform quantization, yes, uniform quantization is quite useful, but, but there are problems. And those problems can be very significant because as we know that if you're talking about a speech or a voice signal will be comprised of various various crest values, and that crest values will always be on the higher side. What is the crest value or the crest factor is quite important in this quantization levels. Whenever we are deciding a particular quantization level, this quantization needs to be understood with respect to crest factors. Now, whenever we are talking about the crest factors, there will always be the higher values and the lower values. So, the crest factor will be the peak value divided by RMS value of the signal. How much it is varying from the RMS value. So, this is called crest factor. Now, whenever we are talking about the crest factor, this crest factor is always high for speech signal and music signal. For music and speech, it is always on the higher side. Other signals, it may vary and it can be on the downside. Now, if you are talking about the PCM signal, we have already understood that signal to noise ratio of PCM signal can be derived with this equation, that is 3 into 2 to the power 2V into P. Here P is the power of that particular voltage signal. Now, whenever we are saying a particular voltage signal, this SN ratio needs to be understood in decibel range. So, 10 log 10, 3 into T 2 to the power 2V into P. This actual equation will come as 4.8 plus 6V dB. Whenever we are using normalization, then P becomes 1. That power factor will become 1. So, unit power factor will decide that the normalized quantization. Now, in this value, whenever we are putting this, so we have to calculate P2. So, whenever we are talking about the P is V maximum square upon R. That is the normal way of calculating anyone's power. Now, if you are talking about V maximum divided by R, so that whenever we are using a normalization, this will be comprised of x square t, because this component will be comprised of x factor xt. So V maximum is x square t divided by r. Now x square t divided by r will become x square t, because whenever we are using a normalization, this r resistance will be comes as input value. So input voltage and this voltage will be same. So R will be of 1 or unit. So 1 ohm will be there. So P comes as x square t. Now we had this equation, crest factor is x maximum upon x square t, as we know from this one. The peak value is x max and RMS value is x square t 1 by 2. That is the root mean square value of all the factors, all the voltage levels. Now whenever we are calculating this thing, as we know, x square t is basically this power. So we will replace it, x maximum divided by root p. Now whenever we are doing the normalization, this value of x maximum will come as 1. This is a very important factor. Whenever we are doing a normalization, all the values above that particular level will be deleted. So x maximum becomes 1 and this equation, this crest factor becomes 1 upon root p. Now this equation is 1 upon root p. Now we have this equation, crest factor, and as we know, this crest factor is very high for speech and music. So whenever it is very high in speech and music, so whenever we are actually, if this value is on the higher side, if this value on the higher side, what will become of this one? If this is high, if you're talking about this one, needs to be higher for speech and music signals. So this means if this needs to be higher, this needs to be on the lower side. So this P will be on the lower side, and it can be shown as P will be very less than 1. When this is very less than 1, then this crest factor becomes high for speech and music signal. Now when we are taking P very less than 1, we are just using this value over there. Now look at this one. If you are talking about this one, in this particular equation, the P is there if it is on the lower side. If it is on the lower side, so what will happen is, so Sn, if you are talking about that equation, 3 into 2 to the power 2v into P, Sn 10 log 10, if you are talking about dV, 3 into 2 to the power 2v into P, which is very less than 1, will always be very less than Sn 10 log 10 3 into 2 to the power 2v into P. If the P's value is normal and this P is very less than, so if you compare both the signals, this particular signals Sn ratio will be very less. So if you are saying this particular signals value will be very less, Sn ratio will be very less, what it implies is actually the noise part will be on the higher side and the signal part will be on the lower side. Whenever in any signal Sn ratio is very less, then that always means that the particular signal part is on the lower side and noise part on the higher side. Now if we have the high noise part, how we are going to mitigate that, how we are going to delete that or address that particular situation? So we cannot use uniform quantization. What we will use is, whenever there is a difference in value, we will increase that step size or decrease that step size. By decreasing and increasing in step size, we can handle this noise part. So whenever there is a high crest value is available to us in particular signal, what we can do is we can actually increase that, and the quantization level will be different, quantization step size will be different. So that is why we use non-uniform quantization and these kind of techniques. Now to address this particular equation, what we are going to use is companding, and that companding is itself a different topic in this particular PCM topic. So whenever we are saying that we cannot use that uniform quantization, we will have to use non-uniform quantization, and this is the reason we have to use non-uniform quantization. All you need to do is you need to note it down first and understand we are doing this because of high crest factor. This is the actual reason we are using this non-uniform quantization level, because in speech and music this problem occurs. In other signals it doesn't. So next topic that will need to be understood is companding in PCM and how it's going to be done. Thank you guys. Now we already know that there is a problem in this uniform quantization, and to understand and just to mitigate that problem, what we need to do is we need to use this adaptation of different quantization levels. Now non-uniform quantization levels can be achieved by actually making a variation in step size. Now how we are going to do is, the technique is called companding. This technique is quite useful in PCM, and this is the most important technique for PCM. Right now, every now and then, people in examination they are going to ask the question about companding, because this technique has been quite widely used throughout the world. Now, what is the meaning of this companding? Actually, what they have been doing is they have been doing compression and expansion at different side. Whenever we are talking about the transmitter side and receiver side, they are doing a different technique. What is the easiest way to actually achieve this non-uniform quantization level is, what you need to do is just steps needs to be make smaller for smaller amplitude, and for the higher amplitude that step size needs to be increased. So the first method by which you can do is putting a distortion at the transmitter side, and again that whenever you are using after quantization, you use at the receiver side, you use the distortion less technique where the distortion needs to be removed and you will have it. But that technique doesn't give us the result as we required. So what will happen is, what we need to do is use this companding. In this technique, we use the compression techniques at the transmitter side and expansion or expander at receiver side. By this method, we can actually check and actually get the required results by variations in step size. Now you can see this is the curve of this particular quantization and the companding technique. This is the linear curve. The middle one is the linear characteristics of any signal. Now what you have is, you can have this expansion over there and the compression over there. Compression happened always at the transmitter side and expansion happened always at the receiver side. This is the VI and V output characteristic signal. So you can understand that this will be the output and this will be the input signal. Again, if you go into this side, the compression is happening is again at the transmitter side and expansion is happening at receiver side. By this you can actually change this adaptation. You change this adaptation of the step size and you will have a better signal to noise ratio signal at the receiver side. So that there will be lesser distortion, there will be a better step size choosing, and you will get the distortion less signal. Now this technique or this actual method is by using companding in non-uniform quantizer. This is the method by which you have been using non-uniform quantizer technique in PCM. In this block diagram you can understand the compression is happening at the transmitter side, then uniform quantization done. After this at the receiver side expansion happened and you will get the required output. Now there are two types of companding. The first one is mu law companding and the second one is A law companding. Whenever we are talking about the mu law companding, this mu law companding is where the compressor characteristics are continuous and in that compressor characteristics are piecewise. So there will be a uniformly compression done at transmitter side in mu law companding, and in A law companding it will be done piecewise. There are different methods by which you can achieve this companding, this compression and expansion at transmitter and receiver side. Now if you want to calculate this one, so V output can be understood by log 1 plus mu m divided by log 1 plus mu. This is the characteristics where m is the input signal and V is the output signal, output characteristics and input characteristics, and this is how this mu law companding constant will actually help it. Now when we need to calculate it, the variations, we need to do this by this manner, dm by dv and log 1 plus mu upon mu 1 plus mu m. It will be calculated by this particular method only. Now if you are talking about the A law companding, in A law companding this compressor characteristics are actually piecewise, so there will be variations by which you can achieve that. Now how it is done is V output is am 1 plus log a till the time if value of m is less than equals to 1 upon a, till the time the value of m is less than 1 upon a. After this equation changes, the V output is 1 plus log AM, 1 plus log A, 1 upon A till 1. So till the time the value of M becomes 1, this output will be shown by this particular equation. Now again we will take the derivatives. We will understood how this is work. So dm by dv is 1 plus log A by A from this equation only, 0 to 1 upon A, and 1 plus log A, 1 plus log A M, that is 1 upon A to 1. This will be the derivative equation of this particular equation. Now I will show you the characteristics of this mu law and A law characteristic. Till the time you can actually note it down, the values and the equations of this particular method. Now how you are going to do, how you are going to show. This is the normal curve of this companding, as you have understood. In mu law characteristics or mu law companding, what you are going to do is so I will draw first the mu law companding in this. This is normalized input, that is M, and that is normalized output. When mu is 0, this will be look like this, the linear characteristics. When the value of mu equals to 5, suppose we are taking the value of 5, so it will be done like this. And if mu is 100, the output characteristics will be like this. As you can see, with respect to input, the output is compression and expanding as per your particular method, or it is quite uniform. This compression technique is quite continuous, so it is continuously increasing all the time, as you can see over there. So compressor characteristics are quite continuous in this particular method. This is the mu law. Now the next one is A law. In A law, whenever we are saying A law, I will draw it over there. So linear characteristics will be shown like this. When A equals to 1, A equals to 2, and when A equals to 100. Now you can see the changes in the curve itself. The way in A type or A law companding is quite different from this mu law companding. In this, the characteristics are quite linear and they are continuous, but in this it is piecewise. There is quite a significant difference at lower level and high level. So whenever there is a difference in low level and high level, you can see that this is A law companding and this is mu law companding. Whenever there is a continuous characteristics, it is A mu law, and whenever there is a piecewise characteristics, differential size, step size will be used, then it is A law characteristics companding. Now this continues for speech and music signal. This mu law compression is used. Mu law this is used for speech and music. This is used for speech and music, and without companding, as we can understand, the PCM performance with mu law companding, if you want to understand the Ashen ratio of that particular signal, SN ratio of that particular signal will be shown like this. Now this is the signal level and this is SN. Without companding, this characteristic will be look like this, or with companding it will be shown like this. This characteristics is without mu log companding, and this one is with mu log companding. So we have two different methodologies. If we don't use mu log companding, the characteristics will be uniform and uniform quantization will be there. So due to this, the lower signal will have lower SN ratio, but in this even the lower signal has high SN ratio. So by using this technique, we can actually achieve the better and noiseless signal, less noise signal actually, because there will be a noise part. Some part will be there. You cannot mitigate the whole noise part, but yes, it will be mitigated to the levels that is quite achievable and that is quite usable for us for music and voice signal. That is all for the day. The next topic is delta modulation, and in this delta modulation and this differential PCM will be understood by using these techniques only. First, we need to understand that companding, how the companding has been used, and the next part will be the use of these techniques in delta modulation. By this, you can achieve a better modulation of that particular PCM signal. Thank you guys. Vande Mataram. Stay home, stay safe, and just follow the government guidelines. Bharat Mata Ki Jai.